I'd like to invite our next team up, disaster response floods. The question they were asked: can we use satellite data and ground truth to better understand flood behavior? So please come on up.
Hi, thanks for having us here today. So we are the floods team. So just before we get into it, I just want to briefly give you a quick introduction to the whole team. So we have Andrew Annex, myself, Diana Donoghue, Chelsea Sedrain, and Dylan Fitzpatrick. We also want to give a big thanks to our mentors. We have Piotr from the University of Warsaw, also from USGS, Jonathan, Theo, and Jack, and also Yaron, Bashali, and as well Guy, who are great help throughout the whole process. So floods are one of the most deadly and destructive natural disasters that can occur in the US and worldwide. It is one of the most common and widespread weather-related disasters that can occur, which because of this, up to 140 deaths due to flood-related incidents can occur. Not only this, but worldwide, people spend up to 250 billion per year just on flood-related incidents, which could be because of structural damage due to health or also agricultural loss. And as you can see here, compared to just globally, compared to natural disasters, floods are the most common and over time period are increasing in frequency. So to deal with this major disaster, what are people actually doing at the moment? So some hydrologists use physics-based models to predict these floods. The problem with these predictions is that it requires a lot of on-site calibrations per site for these, which are extremely difficult because of things such as levees, culverts, and dams. So not only is this very time-consuming, but is also extremely costly. And because of this, there is a lot of areas in the US that cannot avail of these services. So the USGS at the moment have over 11,000 stream sites spread all over across the country, which give updates every 15 minutes of the stream heights, and with some data sources going back as far as 50 years. So leveraging this vast amount of data set and incorporating with machine learning tools, this leads us to the question of can we actually develop on the methods that are being used at the moment to develop a model that can generalize not just for one site, but for a lot of sub-sites all over the US. So now you probably ask, how are we actually going to predict this flood susceptibility? So we have broken down our project into two separate problems. The first is prediction of time to peak. So when a major rainfall event occurs, we want to know how soon after this rainfall will the stream actually reach its peak height. And the reason that this is so important is that if we know when this peak rainfall will occur, this will give people a chance to evacuate the area and can save lives and reduce damage structurally as well. Not only this, but per month, we want to look at, given a stream site, will it reach a given flood threshold at least once? These flood thresholds are monitored by NOAA and are stream site specific. This as well is extremely important because if we know this, we can allow for cities and towns to better prepare for when a flood actually occurs. And on that note, I'm going to pass you to Dylan.
Okay, thanks, Dan. So one of the really exciting aspects of this project is just the huge amount of data that is available to us that actually might help us do better predictions of when and where floods are going to occur. So this was a really exciting part of the project that where we worked hand in hand with our project partners. And we ended up selecting 8 different data sets that really cover a variety of aspects within a region of attributes that are just predictive of really how water might flow through an area. So these data sources range from rainfall data at a high temporal resolution. We have river basin characteristics like the amount of vegetation cover in an area, potentially the amount of impervious surface cover, so how much pavement we have in a location, the soil type, all of these factors that tell us really how water might drain into the groundwater. And then we also have remotely sensed data collected from satellites on land use and topography. And we really saw these data sets as having the most potential for helping us build a set of prediction models for flood susceptibility. So then we get to the really fun part for machine learning researchers, which is to really play with these tools that we've learned all about in school, and we get to really see what works best in the specific domain that we're looking at, and with the specific set of data that we've selected. So for our project, we have applied convolutional neural networks and also tree-based methods like random forests and gradient-boosted decision trees in order to achieve these two specific goals that Diane mentioned. So the first one being for a specific gauge location, and within a given month, can we predict whether there will be a flood in that month, whether we've crossed this flood threshold as defined by NOAA. And then also in a separate model, can we actually predict the time to peak river level after an extreme rain event occurs? And to dive a little bit more into that one, I'd like to talk about a specific use case for this time to peak prediction. So you can imagine that we have an extreme rain event with intensity focused at, say, 4 in the morning in this example. We might have a little bit of an idea ahead of time that this is on its way through weather forecasts or other signals that we get ahead of time. And so we can actually deploy our time to peak prediction model to get a sense for how quickly the waters will rise. Is this going to be a flash flood, or will it be a more sort of longer duration event? And this is really useful information in terms of figuring out how fast we have to act. How much resources do we have to deploy right away in order to get people to safety? So we can look then actually at the actual peak time, and we can see that we did fairly well in this example. We did a good job of predicting how long the river will take to reach its peak height. And so really what this provides us is another early warning system for these flash flood events. So even if we can provide an additional 20 or 30 minutes of lead time for, say, a family that needs to evacuate, that can really mean the difference between life and death, and can mean the difference between protecting your property or loved ones from being harmed throughout this process. It really provides a tool for communities all around the world who are at risk from these flood events for evacuating safely. We also have this monthly flood prediction model that Diane discussed earlier that gives us really an entirely separate tool for more longer term planning for flood response. So here we see an area of northern New Jersey where we're just displaying the predictions that we've made at gauge sites. And we can see that we get some of them correct and we miss on some of them, but that's okay. Really, the target here is to just do a bit better than the baseline status quo. And really what this gives disaster response agencies is this tool for long-term planning. So in locations where things are changing over time, potentially development is occurring, we have the potential for vegetation loss. We could even have changes in rainfall patterns due to climate change. The flood risk changes in these locations. And so these agencies that are tasked with prioritizing where to spend resources in order to plan for disasters really need a model that is sensitive to these changes at a regional scale. Okay, so far we've talked about models that really rely on this data-rich environment that we have in the United States, where we have this extensive network of physical stream gauges. But of course, floods happen all across the world. They even happen in the US in areas where we don't have these stream gauges. And so we'd like to be able to do something in these ungauged areas as well. And so we are really enthusiastic about this idea of actually using high resolution top-down imagery in order to estimate the height of a river or a stream from a remote sensing perspective. So you can see on these images that are flashing by that actually changes in river height result in some observable changes from a top-down perspective, where you might see a sandbar sort of appear or disappear. You might see some beaches appear on the edge. These are the sorts of things that ML tools, machine learning tools, are really great at picking up. And so we're really excited about this work. And we've begun some work in this area, but because it's such a big problem, we've decided to open this up to the machine learning community at large as the Ungauged Basin Challenge. So we have collected a data set of metadata on 6 million images at the 11,000 USGS stream gauge locations, tied to the actual stream height measurements at those locations and at those times. And so the hope is that by releasing this really difficult challenge to the community, we can hopefully make some headway on this hard problem. We've also been in discussions with the floods team at FDL Europe on using machine learning to produce calibrated flood and inundation maps for at-risk communities all over the world. And so this harkens back to the physics-based models that Diane mentioned that require a lot of location-specific hand tuning that can be very expensive. The idea is, can we calibrate these models using machine learning in order to increase the applicability across a much larger scale? Okay, so to summarize, we've made some really exciting steps towards real-time river level predictions. And these state-of-the-art machine learning tools and the vast array of data sets that are at our disposal can help disaster response agencies do a much better job of responding quickly and effectively once these events actually occur, thereby reducing their economic cost and hopefully saving lives. So we'd be really excited to talk to you more at our poster session. Yeah, let's talk later. Thank you.